Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled Unit 6 Review. Okay, can you feel it? I certainly can. I feel that we're incredibly close to wrapping this thing up. Let's put this thing to a test here and see if you've made use of some of this information that's coming out of the internet or if it's spilled all over the floor. We went over common functions of combinational logic, and what we'll do is just walk through a brief example of each one of these things, and let's see if you're understanding what we're talking about. First one is our digital principles that's applied to motor controls. Then we'll move on to adders, multiplexers, demultiplexers, comparators, all those code conversion functions we talked about, encoders, decoders, code converters, and finally parity. And if you understand what we're talking about this review, I'm pretty confident that you can make it through. We're going to put in application some of the VHDL principles and techniques that we learned in lab here. But what I'm looking for right now in this Unit 6 review is just an understanding of these common combinational logic functions. Okay, first one, digital principles applied to motor controls and PLCs. All right, your boss comes up to you and he says, Johnny, I want you to efficiently implement the expression X. And what is X? X is A and not B and not C, or A and B and not C, using ladder logic. Okay, so you're using a traditional motor control scheme. You're going to use general, normally open contacts, and normally closed switch schematic symbols. Assume that the X is a lamp. I don't know why I didn't spell out lamp. Must be pressed for time. It's a lamp in the same rung. It could be a coil or something like that. Just for this one, it's a lamp. And knowing what you know, where normally opens versus normally closed. A normally closed is kind of equivalent to a NOT gate. A normally open is a regular input because again, it's the activated versus deactivated. If it's deactivated, we're giving a 0. If it's activated, we're giving that switch a 1. And when they are, so that's their deactivated state. And when they are activated, what happens to a normally open switch? It closes. What happens to a normally closed switch? It opens. Closes, opens. Ands are series connections of normally opens or normally closed switches. What is an OR? An OR is a parallel connection. Looks like we've got an AND with some negations. So that might be a series. An AND with some negations, that might be a series, with an OR in between, so that might be a parallel connection. And you may be rushed to a certain judgment where you've implemented the following circuit, where it is completely wrong. What is this expression? Yes, it is implementing X, which is A and not B and not C, or A and B and not C. Because what you missed was your boss is implying to efficiently implement the expression X. All right. What you failed to take in consideration with this, which is it's totally correct as far as motor control goes using ladder logic, you failed to recognize that there's some Boolean simplification that can occur. And what I want to do is just compare and contrast what we've developed here. So we've got a series rung. A ANDed with not B ANDed with not C, or A ANDed with B ANDed with not C. There is a common term that we could potentially take out of this thing. We could factor out of here and somehow simplify this incorrect version we came up. And notice how I've included wire numbers here. Here's L1, here's 1, 2, 3. And 3 is actually a common connection for both parallel rungs. And I've got 4 and 5. And obviously I've got L2. So in this here, I've got 7 wires, 6 switches, and obviously 1 output. Do the Boolean simplification that you see. Okay, what I see is a common term, A and not C. I'm going to pull that out. What I get is not B or B. Does this look like something? That's 1 from our Boolean rules. What is 1 ANDed with anything? In this case, it's A and not C. So the expression X could be better written as A and not C. Go ahead and try to do the ladder logic description for A and not C and compare and contrast it with the inefficient implementation which we came up earlier. So you should look something like this. So I've got L1, wire 2, L2. So I've got 4 wires. How many contactors do I have? I have 2 switches. I've got 1 output. Why is it a series connection? Because it's A ANDed with not C. Why is C a normally closed contact? Because it's a not C. And it's implementing the exact same logic as we did over here. Compare and contrast the savings in not only equipment, switches and wires, but the time it would take to implement that. So it's a pretty cool example here of some of the basic concepts of ands being in series, ors being in parallel, normal close contactors being in negation. Just some of the principles that we've discussed thus far. You have to be able to recognize some of these Boolean rules to obviously implement it more efficiently. Okay, let's move on to a discussion of adders. And in this particular example here, we're going to try to connect 4 full adders to perform parallel addition of 2 4-bit numbers. And we're going to use for this particular example is A and B. And they are written MSB to LSB, just like you'd expect, left to right. I want you to show the inputs and the outputs and all the carry-ins and outs. I want you to clearly label the MSB, the LSB for the inputs and the outputs. Obviously, step 0 is connect them. How are these things going to work? How do those 4 full adders work to perform parallel binary addition? If we remember right, the carry out of the low order feeds the carry into the next. So what you've got to do is figure out who's the low order. Just pick one. Which one's the low order? There's an easy way to do this. There's a hard way to do it. The easiest way I'm going to do it is if I've written MSB to LSB in that direction, why not just organize those things in that same direction? I don't have to do any crazy wiring. This is now my low order adder. That's my high order adder. If this LSB adder, its carry out feeds the carry into the next significant bit. This one's carry out feeds the carry in for the next significant bit. This one's carry out feeds the MSB carry in. Okay, so that's step 1. You got to go ahead and where do those carry outs go? Now, where does the carry in for the LSB? Namely, this guy right there. What's the LSB? There's nothing being carried in. I've got to go ahead and give that a logical 0. Okay, place our inputs on there. Where are they going to? Well, I could put the A's on the A's or the B's. It doesn't matter because those inputs for the full adders, they're just labels. It doesn't have to be that way. But I'm just going to make my job easy. I'm going to put the A's where the A's are and put the B's where the B's are. And again, which one is the LSB? Which one's the MSB? This side is the MSB. That side's the LSB. This is the lower order adder. So I'm going to put A0 right there, the LSB. A1, A2, all the way up to A3, the MSB. Same thing here. 2 LSBs get added together. And moving on to the NSB. I love that. The next significant bit. And finally, all the way up to the MSB. Where are my outputs? Well, if the 2 LSBs are being added together, it stands to conjecture that is my sum LSB, sum NSB. And finally, what is my carry out for this whole 4-bit adder? It's that carry out. If I was to keep this as just a 4-bit adder, let's say I'm not going to use this for perhaps 8-bit addition later on, I could just say that that is now my MSB. And now really just put those numbers in there. Okay, what is A0, A1, B2, B, all those numbers in there? Just put them in there. So there's my A's and there's my B's. Okay, go ahead and figure out what the sum and the carries are. Okay, so what I'm asking is put the intermediary values from one stage to the next. I'll go ahead and put some spaces here so you know what I'm talking about. There you go. So what is carry out of this stage? The carry into the next. What's the carry out of that stage? Carry into the next. Carry out of that stage, carry into the next, and go ahead and fill out those values. And obviously these guys right here. And the point of this is do you really know how a full adder works? Do you know how a full adder works in combination with 4 other full adders to produce a 4-bit parallel binary adder? You should have values like this. For the first stage, it's adding 1 and 1 and 0. What do I get as my sum and carry? It's going to be carry out and sum 1, 0. Because then think about it. It's 1 plus 1. What do I get as an output? I should be getting 2 as an output. 1, 0. Binary equivalent. So do that for the other stages. You should get something like this. And there you go. Okay, so if I'm going to read my number, my output, 0, 1, 1, 1, 0. Does that make sense? If that's the LSB and that's the MSB, we've got 8, a 4, and a 2 as an output. What is that? It's 14 decimal equivalent. Does A plus B make 14? Just think about it. Does 5 plus 9 make 14? In my world, it certainly does. Has your adder functioned correctly? Yes, it has. Again, it's just how does a full adder work? How does a full adder work in combination? Let's go ahead and see if you can knock out this example right here. What I want you to do is add positive 5, and for the number B, I want you to add negative 3, but I want it expressed in 2's complement. So again, this is a synthesis of materials. You got to reach way back to Unit 2 and figure out, okay, what is the representation of a negative number in 2's complement? How do I use this for addition and subtraction. So first off, what's the first steps? Express the numbers in their regular binary. And in the case of B, what we got to do is I got to express 3, and then I'm going to have to go ahead and invert 3 and add a 1, and that is the 2's complement representation. So let's go ahead and do that. So your representations for for A and for B should look like this. There you go. So A, real easy. B, I have represented positive 3, I inverted it, and I added a 1. Now what do I go ahead and do with those guys? I add them together, and then there's a final step that we got to do for 2's complement. So let's go ahead and hook up our 4-bit parallel binary adder in the correct function. And let's go ahead and designate that one as the LSB. That one is the MSB. It's going to simplify our wiring. And I'm not even asking you to put these numbers on here. Just wire up the adders. Okay, you should remember this from our previous example, like done a minute ago. It should look something like this. First step, LSB, ground that carry input. Connect the carry out from the LSBs to the carry into the next. Carry out of that one, carry into the next, carry out of that one, carry into the next, so on and so forth. Okay, now put the numbers on there. Where does A go? Well, MSB, 0, 1, 0, 1. Where does B go? 1, 1, 0, 1. What is these inputs? What does it produce for that output and that output? Should look something like this. There you go. What does the next stage's outputs do based upon its inputs? There you go. And go ahead and just keep on working down the line. You're going to get this, and I'll stop at the very end to show you something neat. There you go. We've got all our sum outputs, and what is our final carry out when it is adding 0, 1, 1? Should be a 1, but what was our final step in 2's complement? Using the 2's complement to do subtraction, discard it. What's our answer? Just take these guys right here. Is that the answer we're looking for? Does 5 minus 3 equal binary 0, 0, 1, 0? i.e. 2? It certainly does. So it's pretty cool. We're using a synthesis of what we learned in Unit 2, just what we just learned in Unit 6 about parallel binary adders. And yeah, it works. All you do is just go ahead and represent those numbers. How would I represent the number B in 2's complement? It's right there in the steps. Put 3 in there. Invert it. Feed it to 4 inverters. Add a 1. Have a 4-bit binary. This is a 4-bit case. Obviously, if we did 8-bit binary, we'd have to add 7 zeros with a 1. In this particular case, just hook it up to an adder with 3 zeros and a 1 on it. Okay, so you can generate 2's complement numbers in the negative of a number using stuff we've already learned about. You already know about inverters. You already just learned about adders. And then we're going to use an adder to perform subtraction. Pretty cool, huh? Okay, let's move on to our next topic, which I cannot remember what it is. Multiplexers and demultiplexers. Actually, wait. I got one more thing to talk about adders, which we have not discussed even in our previous lectures. And this is kind of neat here. It's this concept of ripple. Think about this. This carry out, that carry out, that carry out. It takes time. Think about that. 8 bits. I'm going to try to represent those 4 full adders in a box to create a 4-bit parallel adder. And then another one here. Think about this one's carry out. It's that one's carry in. If it took me, I have to generate the low order, the next, the MSB for that carry out to happen. It's creating this potentially disastrous delay, which is occurring because this one right here can't generate any of its values until this one's done. So how you do that is this concept of fast look ahead carry. This carry out feeds that carry in. This carry out feeds that carry in. This carry out feeds that carry in. Where's this one's carry out? Well, it's not there. It's generated by this fast look ahead carry. And I'm not asking you to do the logic for this because it's a nightmare. I had to look it up. The fast look ahead carry generates the whole 4-bit binary carry out, that one right there, based on all these inputs simultaneously. Okay, and I'm actually missing a wire there because there should be a wire to that carry in. And what the logic is this. This is why I'm saying don't worry about the logic. And I had to look this thing up. The carry out for a 4-bit binary adder is generated simultaneously. As soon as those inputs A0 through A3 and B0 and B3 and C are put on those inputs, this is instantly generated. So when you hook it up in this fashion here, you've got that number right there. You don't have to wait for that stage, that stage, that stage, that stage, then finally getting that carry out. So that's what's known as fast look ahead carry. If you didn't have a fast look ahead carry, that's what's called ripple adder. It's kind of what it's doing. It's rippling through. It takes time for those waves to propagate. Whereas with a fast lookup, you got it instantly, and you can use it in this larger combination right here. Let's go on to multiplexers and demultiplexers. So let's talk about our next common function of combinational logic, namely our multiplexer and demultiplexer. So what I've got the multiplexers and demultiplexers set up here is a great application for what they're built to do. They're basically taking parallel data, routing it onto a serial line, and this is our serial line stretching across space and time, and the demultiplexers at the end are taking that serial data and expanding it out into parallel receivers. So what is a multiplexer? It's a parallel to serial converter. What's a demultiplexer? It's a serial to parallel converter. How do they know who is sending and who is receiving? These address select lines, S1 and S0. Additionally, notice how I've drawn the diagram. It's a structural implementation of a 4-to-1 multiplexer using 3 2-to-1 multiplexers. And this is a great problem, kind of the who's talking to who problem. And the most important point of the who's talking to who problem is right here. I want you to figure out at that moment in time who is talking to who. And the answer is Satan is talking to Boylestad. I'm going to say that answer again. Satan is talking to Boylestad. So let's move on to our next common function of combinational logic circuits, namely our combination of decoders, encoders, code converters, and parity. We'll wrap up this Unit 6 review. Okay, so here are some common functions of combinational logic circuits on the left-hand side, namely the decoder, encoder, code converter, and parity. And here are some descriptions on the right-hand side, not necessarily in order. Go ahead and see if we can draw the line from the name to the description. So code converter, that's kind of the translator. It's taking binary, converting it to gray code. The example we did was binary to BCD and vice versa. What's the next one? Which makes the code? How about an encoder? So you can press a key and it's going to output the ASCII code for that. A keyboard is an encoder. Which one error checks? I would call that parity, okay, because what I'm doing in the example that I used was an even odd parity checker and generator. And then finally, obviously, what the only one's remaining is our decoder. It recognizes the code. Okay, let's just do a quick example of a decoder. Let's see if you can create a 3-bit active low decoder for all possible combinations of 3 bits. So obviously I'm going to need 8 NAND gates to do that. These are typically called 3 to 8 decoders because again, what have I got? I've got 3 inputs, 3 bits. How many possible combinations can I get for 3 bits? It's 8. Okay, so I have 8 outputs. What do I feed to every single one of the inputs? Well, all 3 bits. B0, B1, B2. However, those inputs to those particular NAND gates must be negated or left alone, so only one of those outputs is active at any time. So for example, 000. What I'm going to do is just invert all 3 inputs. How about 001? Invert the 2 MSB inputs. And ultimately my combinations are going to look something like this. There you go. Okay, so this being B3, B2, B1. Actually, let's do it this way. There you go. Okay, so B2 is in red, B1's in blue, B0 is in green. And if I'm in fact in combination, let's say 0, 1, 1, which is the only output that is giving me an active low, it should be this guy right there. And you could potentially string up a bunch of LEDs to these things, syncing relationships that would indicate the presence of a particular number. This one being 0, 1, 2, 3, 4, 5, 6, 7. And if you want to get fancy, you can go ahead and do a 3-bit counter and make yourself a really fancy Christmas display. And what would happen is the lights would just progress across, recycle, progress across. Pretty cool application around the holidays. Let's just do an example of parity. Let's put some 1s and 0s in there. Let's say I've got an 8-bit number that I want to send to my buddy using odd parity. Here's my 8-bit number, 0, 1, 1, 0, 0, 1, 1, 1. Okay, so what is the parity bit that I need to append to this 8-bit stream using odd parity? Okay, so parity, if you remember right, it's a means of error checking. And what I'm going to do is append appropriate bit in this particular case to make it odd. The number of 1's odd. So I see 1, 1, 2, 3, 4, 5 ones. It's already odd. My appended bit in this particular example is a 0. So when that is transmitted, all 9 bits of that, this parity bit can also be used in the checker to, in the event of an erroneous transmission, say for example that bit is erroneously transmitted as a 1, and if I'm using odd parity, what I see is 6 ones. That's not odd, so I know that there is an error. Okay, my parity checker would indicate, okay, this transmission error has occurred. Okay, that about wraps up our review for this section, Common Functions of Combinational Logic Circuits, and really represents the synthesis of pretty much all the units previous to this. Hopefully you did pretty well, and we will move on to the next chapter on our digital electronics education.